So now that we've kind of looked at some of the key features of them individually, let's look at them together. So again, let's remember that ln is log base e, uh, log x is log base 10, and this is obviously log base 2. It states it right there. So in order to kind of get a better understanding of this, let's talk about what E is. So let me grab my pen here. So again, we're rewriting this as log base E. And again, E is a number that's discovered in nature that occurs a lot. I believe it's 2.7. Let me grab Desmos here. So E is 2.71. And they keep theoretically going on forever. So 2.718. I feel like that's enough digits. So let's think of it as log base 2.718. So this is our F, which I should have done in red because they're color coding it red. So let me change my color here. Log base 2.718 of x. And you can see it's right here in the middle. And what that's telling us is that it's growing in between log base 2, and if we go on green, this is a regular log is known as log base 10. So what we can see here is that at first our growth is it's happening a lot faster. So if we look at log base 2, it grows faster than the other ones. And the reason why that is we're dealing with essentially negative power. So remember, if we're talking here in this negative side, if we were to inverse this, what we're really asking is 2.7 to what power gives us these negative y values that we're getting right here. So what's happening is it grows faster because these are negative numbers because they grow at negative rates. So it's very kind of weird to think about how it's growing, but all you really need to understand is what's happening afterwards. The bigger the base, the faster it's growing. So this h of x is this graph right here, the log base 2. This ends up growing faster even though it's a smaller base. So that's all you really need to take away from it. The smaller the base of the log, the faster the growth rate. Inversely, like if I said 2 to a power. So it makes sense because if we take the inverse of it, if we write it as an exponential instead of a log, it's growing backwards. So again, logs are a very weird topic because we can't really calculate them like we do with exponents. Exponents is kind of like the last math we can write down using multiplication and stuff like that. So just keep in mind that's the basic takeaway you should take from this. The smaller the base, the faster the growth rate. All right. So this, oh my gosh, this looks complicated, guys. Um, but all it's doing is calculating the slope. So it's picking 2 points, an x and a y, and it's calculating how fast it grows. So please do not let this intimidate you. I feel like they're making the theme very complicated. All they're doing is calculating the slope, the growth rate. If they had this, they're taking it from here, and calculating the slope of the line. They're calculating the rise over run. That's all they're doing. They just have these long, complicated formulas that make it seem hard, but all they're doing is rise over run. They're just doing y2 minus y1 over x2 minus x1. So even though it looks really hard, they're just like, hey, I want to take the y value of this. Let me put a different color. They want to take the y value of this, and they want to subtract it from the y value of this. And that's going to be our top. Then we're going to take the x value of the purple dot and subtract it from the x value of the green dot and do it. So y value of this purple minus y value of the yellow is on top. That's our rise. So if we do purple minus yellow for y's, that's our rise. And then if we do the x of the purple minus the x of the green, that's how we get this. So rise over run. That's how we get rise over run. That's all they're doing here. Rise over run tells us how fast something is growing. It's telling us how fast the y is growing over a certain amount of time. So it's our rate of change over, usually x is considered time. Usually our independent variable is what we're measuring over time. So x is usually a form of time. So it's telling us how much we're changing over time. Now we're doing, why do many log functions, these aren't transformed in any matter, a base, have the point that in common? Well, so the reason for this is, why does it always pass through this? And I've talked about this a few times. So if we rewrite this as e to the x, or 10 to the x, or 2 to the x, if we write these out in exponential form, what's happening is we're really asking our y is our x. So e to the 0, 10 to the 0, 2 to the 0. So if we do the inverse of this, which is the exponent form, the y's are our x's. So the inverse is this exponential. When we switch our x's and our y's, we can write them like this. So if we take the inverse of a log, it is an exponential. Since the inverse is where the x's and y's switch, so this is where our x's and y's are going to switch. We are talking about 0, 1 for these exponentials. So if we're switching the x and the y, we're talking about this point. This happens because any number to the power of 0 is 1. So that's why this is happening. This keeps happening over and over. We're not moving it to the left. We're not moving it to the right. We're not multiplying it by a random number. All logs have this point, and that's because logs are just backwards exponentials. So in an exponential, when you have something to the power of 0, so if you have something to the power of 0, so any number, I'm going to call it n to the power of 0, you have to get 1. So any number to the power of 0 equals 1. So if I wrote this as a log of any base of 1 has to be 0. If we take this, what power of n is going to give us this 1? 0. So that's where I get this 1 comma 0. All right. So that's going to explain. I'm sure they're going to have like a long-winded conversation. Yeah. So they're showing it's like, oh, we're going to redefine this. And they kind of do it with K and all this other stuff. All you really have to say, this K is your Y value. So I don't know why they're doing function notations to simplify talking about this. Just think of this as a Y. This is our Y. So where you see K here, there's a Y. So, in other words, and they write it all super complicated. I hope what I wrote makes a little more sense in helping this out. But what they're doing here is they're saying that, hey, what value, y value gives you 1? 0. If our exponent is 0, we get a 1. So that's why that point always shows up in the graph. All right, so here's the thing. If our a, the number in front of it, our coefficient is a negative number, it flips on the x-axis. So this here shows us that changing the coefficient to negative flips on the x-axis. It is also going to change our, it's also going to change, it only changes our, forgive me, it changes our x-axis, or x-intercept, I should say. It changes our x-intercept because we're taking that y value and we're multiplying it, and this 3 is changing it a bit because it's multiplying it. So you can read up right here what's happening. By putting a number here, this would normally pop out some type of y value. But because we're multiplying it by -2, that y value gets multiplied by a different number. This one, this 3 in front of the x, what's happening is normally you plug in an x, you get a certain number out. But before we even plug it into the log, it's being multiplied by 3. So let's say I plugged in a 2. So let's say I plugged in a 2. I'm not taking the log of 2 anymore. I'm going to take the log of 6 because it has to get multiplied by this 3 before it goes into that log function. So that's why these changes are happening. Any change I would do here would have the same effect. So now we're going to be talking about what happens when I multiply the x. So again, we kind of already talked about what this 2 and this ln is doing because it's going to get multiplied. We talked about it over here. But this -3, what's happening here is we plug in a number, and before this ln even gets a chance to talk to it, it's going to be affected by this -6. So even though, let's say you plug in a 1, let's say I plugged in a 1 for my x. I'm not even going to be dealing with that 1 because what's going to happen here is it's going to 2 times 1 is going to turn this into 2, and then I'm going to subtract it by 4, or 6. Sorry, I'm going to subtract by 6, and I get a -4. Well, guess what? I can't have this -4. We said that logs can't be negative. So what happens is it has to shift over here because all of a sudden none of this can happen anymore. The very first time I'm going to be able to do something is with anything higher than 3, basically. Because what's happening here is, let's say I plug in a 3. Then I multiply that by 2, and I get a 6. And I mentioned that ln can never touch the 0 axis. So it has to be something a little bit bigger than 3. So that's how come the graph kind of shifts over a little bit. So that's why the intercept's changing, why everything changes here. So this is kind of talking about a transformation about logs. All right, why is this flipping over? Well, what's happening here is we're making the x negative. So by making this x like a negative, it's going to flip over on the y-axis because um, instead of this 5 acting like a 5, it's going to act like a negative, or instead of this -5, I'm sorry. this -5 right here, we plug it in here, you're multiplying it by -2. It's acting like a 10 now. It's like, oh, wow. So then it's 10 minus 10, you get 0, which will give you technically a 1 for a log, but then we're multiplying it by 3. So all of this weird stuff is kind of happening that's changing it. So that's why if you have a negative x, you can just ignore this 10 for it. If you have a negative x, it's going to flip over. This 10 is moving it over as well. So there's all these things going on that change the graph a little bit, and we're going to deal with those little by little in this lesson. So ln of x. So here's how we normally look at a log function. It has a specific curve, but most of the time our asymptote is 0, our x-intercept is 1, or technically 1 comma 0. So that's how functions grow. So if you're having a hard time understanding me because there's a lot of stuff going on, I really recommend this video. It gives you specific examples to kind of help you work through and understand why logs go to the left, why they go to the right, and how we can better understand how these logs are transforming. So now let's kind of get a little bit more used to using x's. So we're going to do this, or x's, bases. We're going to be using base 2 for the next function. So let's kind of get into this using this new base 2. So we're going to log base 2. Ooh. So let's get into relationship. Let's customize this to make this a little easier on us. So we're going to use this log function right here. Log function. They're going to ask us a little base. You can see it flashing down there. We're going to do base 2. In the parentheses, we're going to do 3x minus 6. All right, so there's our function. Let's plot it. So we can see here that our asymptotes and things kind of change. You can see that this asymptote looks like it's at 2. And that kind of makes sense because let's think about it. Why would this be at 2? Well, our asymptote is normally where log is 0. So let's just try to make this, what's inside here, 0. How do we do that? So 3x minus 6 equals 0. Well, this is going to become um, 3x equals 6, which means that x is going to equal 2. So that's why our asymptote is 2. Now, normally, our y-intercept is when we get a 1. So that part is a little harder to explain how we get that 1 because we want, how do I put this? We want our exponent to be 1. Actually, I guess it isn't that hard to explain. So what we're going to do here is, let me see. Give me a second here, guys. So normally what happens here is our x-intercept is 1 comma 0. So in order for us to get to that, to get to this equals 1 thing here, we want this to be 0. So we already kind of proved that part where we want this to end up being 0. So that's where we get the asymptote. So, what power? If this is 0, then we end up getting the 1. So that's where we get that part. But what happens when our exponent, we want this to be 2. Well, in order for that to be 2, that's where we get this 1. We want this to be 1. That's how we're able to do this. Log of what power is going to give us the same thing. So in order for that to happen, we want this to be 1. That's how we end up getting that 1 comma 0. So let's get into this. So How is this going to happen? Well, in order for this to happen, we're going to have to set what's known, this part right here, as the argument. So we already set the argument to 0. That's how we found our asymptote. So let's set this argument equal to 1. So this is where we're going to get a weird number, because if we add the 6, now we have 7. So x equals 7 over 3, which is why this isn't exactly a 2. It's not exactly a 3. It's kind of in the middle of 2 and 3, because 3 goes into 7 more than 2 times. Very little after that, like 2 and 1/3, because the 3 goes into 6 2 times perfectly, but we have a 1 left over to get to the 7. We need 1 more to get to 7, so 1/3 more. So that's where we're going to get these values from. Again, the reasoning why is kind of weird, but if you ever want to find your x-axis, you essentially want to make your argument equal to 1. That way you can find your x-intercept. If you want to find your asymptote, you want to make your argument equal to 0. So again, this part inside here, we're going to call that an argument. Obviously, there's other things that can affect it, like if you're adding a k over here, if you're multiplying, but for the most part, that's what we're going to be doing. Oops, did not mean to show you guys all that. All right, so what's the asymptote? Well, I already said that our asymptote is 2. And why was that? We made our argument equal to 0. This part, like I said, it's kind of weird to figure out, but we had 2 and 1/3. So a third, if you ever do 3 into 1, you're going to end up getting 0.333333333. So in other words, 2.3333333. Next is our domain. And again, I know you guys can see the glimpse of it, rewind it or whatever, but I want to show you this. So if you look here, it's anything bigger than 2. So you want to kind of start off at 2, but then you go to infinity, right? That's our domain. If we look at our end behavior, it's going to keep increasing very slowly till it gets to infinity. So when we go to the left approaches infinity, right? Oh, okay. So as we go to the left, our y approaches negative infinity. So as we go to the left, it's going to go down. As we go to the right, it goes up. Is this increasing or decreasing? It's increasing. So that's simple, nice, easy. It's increasing. Cool. Oops, I keep doing that, guys. Again, obviously, it's easy to get the answers, but I'm trying to teach you guys through it. So we're going to talk about our slope. We're going to try to calculate slope. And remember, it's x2 minus x1. So what interval do they want us to do? So they want us to go, these are our x's. We don't know what the y's are yet. So we do need to calculate those out. So this is going to take a little bit of work to figure this out. Okay, I was just making sure I had enough time to do this. We're going to have to plug these values in. So you're going to have to make a table x and y. We're going to do 3, 4, 5, and 6 because there's an x value at 3, 4, 5, and 6. I'm not obviously not going to repeat them. So let's get this little table started so we can kind of calculate these out. Unfortunately, they only care about the answers. So that's going to be a little hard to do without showing all this work. I hate that Edmentum doesn't care about showing the work. It's just like, hey, solve for slope. All right, so let me get this started. So this is our function. So we're going to do log base 2. So in order to do log base 2, we're going to divide everything by log of 2. So I don't know if you guys remember this, but in order to write log base 2 of x in a calculator, you have to write it as log base 10 of x divided by log of 2. So at the bottom here, we're going to have log of 2. On the top, we need to write our argument. In this case, our argument isn't just x, it's 3x minus 6. So I'm going to write this as log 3 parentheses minus 6. In this case, oops, what happened here? Oh, I held down the shift key. Minus 6. So whatever I put in the log, that's going to be our x. So the first one, I need to close this. And this one. So the first one here is going to be 3. So I'm going to plug in a 3 into my parentheses. And I get 1.58. Okay, so I get this 1.58. Then I'm going to plug in a 4. I'm going to plug in a 4. And I get this 2.58. So I'm going to write down this 2.58. All right. And then I'm going to put in 5. So I need to put in a 5. So I'm going to write down this 5. And I get this 3.7, basically, 3.17. So I'm going to write down 3.17. And next, I'm going to finally do my 6. So I'm going to change this to 6. And I get this 3.58. So I'm going to get this 3.58. And now, luckily for us, since if we're doing this one, our x2 minus y2 is 4 minus 3. So in other words, that's just 1. So luckily for us, because they're doing it in intervals of 1, I can just put in whatever this minus this is. So because we're increasing by 1, our slope is always over 1. Our run is always 1. The rise just changes. So let me try to calculate all of these rises. So here I'm getting an interval of about 1. So if I subtract it, it's about 1. I don't know how specific they're going to, 2 decimal places. Perfect. So it's about 1. From here to here. So all I'm doing is from here is I was doing 2.58 minus 1.58. I got a 1. So now I'm going to do this one, this 3.17 minus 2.58. Now I get a 0.59. So I'm going to get this 0.59, 0.59 if you want to show that. And then I'm going to do 3.58 minus, so clear that out, 3.58, this number right here, minus 3.71. And remember, all of these are technically being divided by 1. So we are dividing by something. We're dividing by this 1. 1 divided by 1 is 1. This 0.59 divided by 1 is 0.9. And then here we're doing that. So that's all we're doing. How much is this increase? What's our rise over run? So if we see here, it is increasing, but it's increasing slower and slower over time. All right, so let's plug those in, and you can see that I got those right. It's the rate of change increasing. Luckily, they were nice, and they gave us the run was always the same, so we literally only had to figure out the rise. All right, and then they show us the work in here. Honestly, it's kind of annoying because they don't show us how we did all this work right here. All right, so what is the average rate of change of the function you computed? What do the average rate of change shows us? Tell us. So what's happening here? So this tells us that the function, the average rate of change, so the average rate of change tells us that over time, so after a while of time, so over time, the function grows slower. So it is still growing. It's not like it's not growing. It's just growing slower. So for example, if you're saving money, like let's say I'm going to start saving off $100 a day, and then you're like, oh, I got this other thing that I have to pay off now, so now I can only save $80 a day. You're still saving money. You're not saving less money. You're just not saving as fast as before. So that's what's happening here. The rate of change is changing. And as always, guys, if you're having trouble with it, write about it here, leave a comment down below. If you don't know how to solve for this, I understand, but the easiest way to do it is to kind of make your X and Y chart. So your inputs and what you would get as an output here, and then you can calculate the slope. So you might have to like work with a calculator and stuff, kind of learn how to plug these into a calculator. All right. So I got a little bit more in this video. Hopefully I can finish this off today, like I said.